13. Any questions? Okay, well then let me kind of get back to chapter 13 and so we're going to kind of be spread out for 13.1 and 13.2. The topic here is going to be vector valued functions. And 2 and 3 space is primarily what we're going to be working in. But at the moment, I'll just do a 2 space because I stand a fighting chance of graphing it. So if I wrote this down, this would be a typical example of a vector valued function. So I have the arrow over the R because what I get in my range are vectors. They can really be any dimensional space, but we will just be looking at the vectors as being in a 2 or 3 dimensional space. If we're reasonably lucky, then I can find a relationship between the components of this vector and stand a fighting chance of seeing what path this would trace out. So x being t squared, y being t cubed, would tell me that if I took x and raised it to the 3/2 power, I would get y. And so this particular function would be sitting along this curve. But notice, if t is negative, you also will get negative values here, so maybe the better way to write this would be x cubed is y squared, and see that this actually would generate a graph like this. Notice that when x is negative, or when t is negative, the y component here becomes negative. So, for instance, if I say, what is r of -1? That would be the vector 1, -1. And the way in which we view these functions is I would locate the vector 1, -1. So coordinates of this point would be 1, -1. And this would be the vector r of -1. On the other hand, if I looked at something like r of +1, that would give me the vector 1, 1. And that vector would be sitting up here. So this would be r of +1. So what I'm doing is I'm drawing r of t in standard position. Meaning its tail is at the origin. And when I do that, the head of the vector is going to trace along a path. So the head of r of t traces along a path. and that will indicate the direction of motion. So time increases, we're going from below to up above. And we're looking at this path with this direction of motion. Okay? Any questions here? In section 12.1, there's any number of really nice matching exercises, which I have spent time on in the past.
To 12.1?
Yeah, in 12.1, what they do is they give you a bunch of different curves and ask you to match them up with various formulas for these functions. These are really good exercises, and I always like going through them, but I have been jammed at the end of every semester I've taught this class, and consequently I'm going to kind of punt on that, but encourage you to look at them. They give you a nice feel for the types of functions that you can write down the formulas for and the kind of pictures that you can get. Okay, so they're nice problems, real nice problems, but okay, so that's essentially the thing that we really want to keep track of, that the way in which we visualize these functions is by looking at the path that the head of my vectors traces out and indicating the corresponding motion. Okay, so section 13.2 starts moving into the calculus of these functions. So, differentiation, integration. Differentiation, none of these are going to be overly difficult to carry out, but if R of t looked like this, then its derivative we differentiate term-wise. So I would get here 2t minus 3 sine of 3t and 2t over t squared plus 1. No big deal here. Okay, so where does this derivative fit in terms of the pictures? Okay, so here's what I'm going to do. I'm going to kind of draw a generic curve. I could care less if we orient this going left to right or right to left, but let's just orient this going from right to left. So the curve is looking like this. And put some kind of coordinate system on here. And I will tell you that this is R of t. I'd like to draw in R prime of t. So going back to Calc 1, R prime of t is going to be the limit as h goes to 0, R of t plus h minus R of t all over h. H goes to 0 here.
Can you scoop stuff? Can you scoop
Oh,
stuff? Thanks
yeah.
so much.
Okay, just your standard difference quotient. Now here's what I want to do. I would like to sketch in R of t plus h minus R of t over h. To do this, I have to know if h is positive or negative. It matters not, I mean, it matters in terms of the picture I draw, but with this limit, letting h go to 0, h can go to 0 with either positive or negative numbers. So I will do one of those two cases. Any preferences? You want h positive, you want h negative?
Positive.
Positive, okay. All right, so we will take h to be bigger than 0, and consequently t plus h will be bigger than t. So if I go to draw in R of t plus h, will it be to the right of this vector R of t or to the left?
Left.
To the left, because t plus h is farther along in time. Had we chosen h negative, it'd have been over here on the right. So this guy right here is going to be R of t plus h. Okay. Let me draw in R of t plus h minus R of t. Okay, so this could be a test question. I give you two vectors. Here's R of t, there's R of t plus h. You draw in the difference between those two. And the way in which I like to think about it, I think the book even says to do this, write this as plus a minus R of t, because addition is easier. So here's R of t. Down this way would be minus R of t and then I would bring this up like this. So this would be my minus R of t. And that means this vector right here, this vector is going to be R of t plus h minus R of t. Except I really don't want it down here. I would really like it up here. So let me lift that vector up and observe that this, they're not quite parallel because I'm off in lengths and stuff, but this guy right here, this is my R of t plus h minus R of t. Now what happens when you start dividing by h? What's that going to do to your vector? Keep in mind,
the length, right? You see?
it's going to change its length. It's not going to change its direction because h is positive. If we were dealing with h being negative, dividing by h would change the direction. Now, whether it expands this vector or contracts it, pulls it in, makes it smaller or bigger, I don't know. That depends on the magnitude of this vector and how big h is. But you divide by h, all that's going to do is change my scaling. So, maybe we end up with this right here. Maybe this is r of t plus h minus r of t over h. It's really the direction that I want. You know, maybe that's not the right guy. Maybe it's way out there. I don't know. But I do want to pay attention to the direction. We're going to take a limit as h goes to 0. Well, as h goes to 0, what is my green r of t plus h going to do? It's going to come around like this. At which point the direction of my difference quotient is going to be like that. And then divide it by h, and maybe it shrinks in, maybe it expands. Let h get smaller still. And basically what's going to happen is the direction of this difference quotient becomes tangent. One extra piece of information, it's not only tangent, but it points in the direction of motion of the particle. So had h been negative, we would have, prior to dividing by h, had a vector back this way, but dividing by a negative number would shoot it back this way. Get what I'm saying? So as h goes to 0, this vector, r of t plus h minus r of t over h, moves to a tangential direction. So here's the picture that we really want. If I have a vector valued function r, and I pick a point on this, say here, if asked to draw r of t is usually drawn in standard position. This would be my r of t. If asked to put in r prime of t, it's going to be tangential direction to this curve, pointing in the direction of motion. How long is it? I don't know. Without more information, I have no way of knowing. But I do know tangential and pointing in this direction. On the other hand, had I picked a point, say here, this would be my r of t at this point. And down in this direction is r prime of t. All right. So this is the way in which we visualize these vector valued functions. You draw r of t's in standard position. Their tip traces out a path with an indicated direction of motion. R prime of t is drawn usually with the tail of r prime on the head of r. And its direction is in the direction of motion. Is r prime dotted with r 0?
Not necessarily.
Not at all necessarily.
It's not orthogonal.
Not in general. There will be times that it is, but not necessarily, not usually. Oops. The 1L. You can see that here. If you took r dotted with r prime, it would be negative, because that angle's obtuse, bigger than 90 degrees. Down here, slightly positive. The angle's pretty close to 90 degrees, but maybe not quite. And it's an acute angle. Okay? In general, this is not going to be the case. There will be instances where that happens, but not at the moment. So, yeah, this is your standard differentiation of these functions. Integration. So before we do integration with vector valued functions, recall. If I write integral of e to the 2t dt, you get 1/2 e to the 2t plus a constant. If I ask you to evaluate this, this is a definite integral. What you would get would be 1/2 e to the 2t evaluated from 1 to 3. So this would be 1/2 e to the 6th minus e squared. There's a difference between a definite integral and an indefinite integral. This first problem can be reworded. R prime of t, f prime of t is e to the 2t. What's f of t? Just a rewording of the integration, and so the answer here would be f of t is 1/2 e to the 2t plus a constant. And the definite integral that can be reworded into questions of the type f prime of t is e to the 2t, and if I said, for instance, f of 0 equals 5, little mini differential equation. So this would tell me f of t would be 1/2 e to the 2t plus a constant. That constant is not, in this instance, going to be 5. Do not assume it's 5.
9/2.
I'll take your word, but what I would observe is f of 0 is 1/2 plus c, and that is supposed to equal 5, so c is 4.5, or 9/2. And I plug that back in here, and I get that equation, or formula for f. So, just a little quickie in terms of notation review of some Calc 2 stuff. All right. If r of t, let's say, is sine of 3t 2 over 3t plus 1, and I want to integrate that. So what this amounts to is I am going to integrate sine of 3t to get my first component, and I'm going to integrate 2 over 3t plus 1 dt to get my second. Now, it is not necessary to write it out in this detail, but I'm just trying to stress component-wise. You can also observe that this could also be written integral of sine of 3t dt times the I component plus integral 2 over 3t plus 1 dt times the j. I mean, however you choose to write it out. These are indefinite integrals. This first integral is going to be minus 1/3 cosine of 3t, but I can't leave it at that. I have to go plus c this is a logarithm integral. Your u here is 3t plus 1, du is 3 dt. So this is going to end up being 2/3 natural log of absolute value of 3t plus 1. And it's an indefinite integral, therefore, not quite. I've got plus c here.
K?
K, or if you want, you can go c1 plus c2. But in some way, shape, or form, you've got to indicate that those constants may not be the same. Or this could be written minus 1/3 cosine of 3t, 2/3 natural log absolute value of 3t plus 1 plus c, as long as you make sure it's a vector. You can't add scalars to vectors, so if you choose to go this route, make sure that the constant you add is a vector. This can really foul you up later on in some other problems. If you start writing things down that are vectors and you write them down as scalars, it's a problem. Okay, a word about integration. Yes, you're expected to know how to integrate. Okay, I am not going to require you to do partial fractions, trig substitutions. You may have inverse tangent integrals, maybe by parts. Okay, routine, what I would consider very routine integrations. If you can't integrate, you're going to have troubles this semester. Not just here, but we're going to be doing triple integrals soon enough, and then things called line integrals towards the end of the semester. If you need to, you go review your integrals. Okay? And I'll try and do a reasonable variety in this way. If you don't understand, ask. The other thing is, I'm going from here to here without putting in between steps. First of all, if you need me, I can easily go u is 3t plus 1, du is 3 dt. That's the u substitution. And if that doesn't get the job done in terms of doing it, this is the actual integral that I end up with. So if you have questions, I will, I'll go through. But here's the deal. If I were teaching you guys Calc 2, I would require you to show me your u substitutions and probably ask you to plug them in and get everything because you're learning. At this point, some of you don't need to do that. If you don't need to do that, then go. The best measure of that is, are you getting the right answer? So what I would ask people to do in a Calc 2 class is different than in here. And if you can simply look at these and come up with the appropriate integrals, that's fine by me. Just make sure they're correct. You need review on your integrals, go back and review integrals. Don't need to worry about partial fraction decompositions, although that technique will be raising its head in a differential equations class. You don't need to worry about trig substitutions. The integrations here should be fairly reasonable. Okay? So, the big deal here is you can go from this directly down to the vector. And if you do that, make sure your constant of integration is added as a vector. If you decide to write it component-wise, either with i's and j's or like this, make sure that those are going in as potentially distinct constants. So you got a little bit of an upgrade over these problems where, you